So he adjusted the talk, the title. So the new title is now posted there. We will try to update the website, and it's all yours.
Thank you very much. Thank you for the opportunity to be here and to give this talk. And yeah, please forgive me for changing my mind. But fact is, this is a result of being here yesterday and listening to the talks that were given and the questions that were asked. And my feeling is, so I am here to give a talk from the free probability side of the workshop. And then I think it is more interesting for these circumstances, like this particular workshop, to give a talk which actually shows pictures and shows calculations with R transforms. And so the other talk would have been great too, but would have been more like about probabilistic symmetries and without pictures, and didn't want you to all fall asleep. So yeah, like this, I can say, look at this, how nice. Yes. So yes, and okay. So I apologize again for this, but I think actually this is a great topic, and well, it's not so new. It's joint work with Jan Gulden and Doron Puder, published a couple of years ago. One thing, however, which makes me kind of bring it up anyway, and it's this paper had an interesting conjecture, which was recently solved by Ferai and Tevenin. So I will explain what was the conjecture, and I will cite their work. So it's very interesting that they could make progress on that. Okay. So anyway, so here is the object. Yeah. So this is a meandric system. This is a meandric system. Look like a nice picture. Like you can think of some like a system of canals. Yes, this is a highway, and then somebody made a system of canals, 3 canals for this particular picture. But the way to think about this for us is actually here we have 2 non-crossing pair partitions. Yeah. So if you cover what's the south of the highway, you see a non-crossing pair partition sigma. If you cover what's the north of the highway, you see a non-crossing pair partition tau. Yes, and these were picked independently, and what they form is a meandric system. So this is the meandric system given by sigma and tau. My notation, yes, let me write it here. I think it is in agreement with what appeared in previous talks and in the courses of Jamie. Yes, so NC of n will denote the lattice, the set, but it's going to be partially ordered. So it's going to end by being a lattice. Yeah. So NC of n is the set of all non-crossing partitions.
Thank you.
That answer question, sorry.
Yes, I think so. I think they were just trying to understand where the difference is given uncertainty.
Yes.
We have another question about tumor studies comparing somatic copy number mutation or variation among Nigerians and Black and white Americans. Were there tumor samples
is there
that
a
were
question
used
for me or no?
all the same
This is not for me.
FFPs such frozen, were they all processed, stored, and sequenced the same way?
Good question. After the Nigeria study, this is the fast protein samples. It takes some time to get fast protein samples. Actually, the study actually much larger. Like these samples, they are plenty. I think the comparison of TGA, they also have the same. They also found fast protein samples. The 6 and deep, I think.
Okay, maybe I can, in the meanwhile. Yeah, so yeah, that's standard notation, right? So non-crossing partitions, and then if every block of the non-crossing partition is a pair, yes, then my notation is NC2 of 2 endpoints, yes, and that's NC2 of 10, yes, because there are 10 points. Okay, and quite relevant is that yeah, these are both counted, yeah, as it was appeared, it was mentioned repeatedly. Yes, these are both counted by the Catalan numbers. Yeah, okay. So this is when you do combinatorics with these things, you do Catalan combinatorics. With meanders, you do Catalan square combinatorics because you pick a sigma and a tau independently from each other. Okay. Yeah. So here's a natural question which I want to pose. Yeah, is you look pick an n, look at all the meandric systems.
Those could be how if they have a genetic pattern similar, and maybe we can look at
so view nc2 of 2n square as a probability space where every atom has the same mass, which has to be 1 over the square Catalan number. Yeah, okay. Then counting the number of components of a meandric system becomes a random variable. Yeah, so we get a random variable in the usual sense. Yeah, let me call it xn. Xn is matrix values in 1 to 3n. Yes, because this is the number, the possibilities for the number of connected components. Xn of sigma tau is the number of components of the meandric system which you create with sigma and tau. Yeah. So so that's a random variable on a probability space. And yeah, silly question. What's the expectation? Or yeah. So what can we say about this expectation when n goes to infinity? So what can we say about the expectation of this random variable? Yeah, and in this paper that I'm presenting, yeah, so by Gulden, Uder, and myself,
and that's reason we did a small study.
We made a conjecture.
Hopefully, we can stand this in the future.
Great, thank you. Switching gears.
That this expectation goes
and then it
like
looks
a constant
that's
time
the
zone.
difference between Nigerian. Do you have any thoughts as to why that must be?
And this constant from numerical simulation is like 0.26. Okay. And what we could prove, yes, so kind of like to have some evidence towards this conjecture, it's good to be able to prove some lower and upper bounds for this expectation. So when you divide it by n, show that the lim inf is strictly positive, show that the lim sup is strictly smaller than 1. Yes. N. N, like in my picture, n was 5 and 2n was 10. No, n, no. This one is the number of components. This is the sign for number. Okay, good. And what we could prove, yes. So let me continue here. So if you do the lim inf and the lim sup, yeah. So we like it seems that that the limit exists and is somewhere around that value, but we could prove some bounds for lim-inf and lim-sup. Okay, so this somehow is evidence towards the fact that indeed the expectation of xn is likely, well, is likely to be like a constant times n. Yes, because it doesn't escape towards one of the ends of the interval 0, 1. Yeah, and here, like this one, which is this is quite rough, of course, and it is easy to. It is given by an elementary argument. Yeah. The other one is using some things about R transforms, and actually this is the one which I want to talk about. Really, like want to show how it comes. Yeah. So this is based on some R transform calculations. Yeah, and I think it's nice to see how this can come up. Yeah. Okay. Now, as I said, in the meanwhile, yes, since then, recently, it's in a paper posted this January. Ferai and Tevenin. So conjecture. The one over there was proved by Valentin Ferai and Paul Tevenin. Limit exists. And it is greater or equal 0.2, less or equal 0.3. So they have estimates for the limit which approximated better than the bounds we had before. Yeah, and this is a preprint on arXiv from January of this year, January 22. Okay, and yeah, and this was the first part of my talk. Okay, so to tell you about this nice structure and this conjecture. And the nice thing, like this is not the solutions, but the problems. I think you can explain them to a gifted high school student. So that's very nice about this. Yeah. Okay. So now I go to something which I did with Gulden and Puder. So we rephrase the problem. Yeah, what we could prove was based on rephrasing this problem of the random variable xn. Yeah, and this is by using the Hasse diagram of NC of n. Hasse diagram is what you would naturally also call, if you wanted, cover graph of NC of n. Yeah, and I'll explain it on an example. Yes, so here is NCO4. These are the 14 pictures that Peilan showed yesterday. Yeah, so 14, but they are organized nicely by block size, and they are put on levels 1, 6, 6, 1. Yeah, according to whether they have 1, 2, 3, or 4 blocks. Yeah, and the Hasse diagram is a graph where these are the vertices. Yeah, and then you draw an edge in the following situation. So first of all, yeah, you have yeah, maybe I keep writing here. So pi rho in NC of n, pi less or equal rho. Yes, this is something which appeared repeatedly. Yes, means that every block of rho is a union of blocks of pi. Yes, this is the reverse refinement. Yeah, so says that actually what you can do is you can start with rho, take some of the blocks of rho, break them in non-crossing ways, and you will get pi. Yeah, this is the inequality. Now, you say that here, you say in this situation, you say that rho covers pi, If rho is greater or equal pi, it is distinct from pi, and there is nothing in between them in the reverse refinement order. Yeah, and actually you can see right away that, given how the pictures work, rho is a cover of pi means that rho is greater or equal pi in the reverse refinement order, and also I'll write this here. Rho covers pi. This happens precisely when rho is greater or equal pi. And if you look at the number of blocks, pi has one block less. No, pi has one block more. Yeah. Okay. So to have a cover relation, you must take exactly one block of rho and break it exactly into pieces, and then there is nothing which can be in between. Yeah. So this is bigger than all these people. Yeah. Okay. And now let's see, for instance, this one. What would be the edges which go from here to the next level? So what you have to do, so then this is the rho, must break one of the blocks, but clearly this one is the one which can be broken, and can be broken in three ways. Can be broken 1 plus 2 in three ways. So either this way, yes. So separate the 1, or separate the 2. Yes, and then separate the second element of the block, which is the number 3 actually. Yeah. So it's going to be this one. Yeah, or separate the 4. Yes, and then it's going to be this one. Yeah. Okay. So there are 3 edges starting from here and going to the next level, and you can repeat this for each of the partitions here, and you get, if you want, so there are 16 edges which you will draw here, and there is a formula for the total number of edges in the Hasse diagram, yeah, which you can I don't know, deduce if you want. Yeah.
Is this the right way around, or am I?
Yeah.
The number of blocks is going down.
Yes. I think yes. I could claim this was a test of your attention, but no, it was an honest mistake. Yes. So rho is the bigger one. Rho is the bigger partition, has fewer blocks. Okay, like this one. This one has 1. This one has 2. This one has 2. This one has 3. Yeah. So okay. So. Okay. Okay. Yeah. Okay. Well, yeah. Good. Okay. Yeah. So I've done this. Okay. And for if you have two elements in the Hasse diagram, you can measure the distance between them like as you usually have the distance between two vertices of a graph. Yeah, and I'll call this d sub h. So if pi and rho are two partitions, yeah, d sub h. So h is for Hasse. dh between pi and rho is the length of the shortest path which you could draw in this graph. If you did all the edges, what was the shortest path between pi and rho? Yes. So for instance, I don't know, like this one as an edge here. Yeah. Okay. So then I looked at the distance from this fellow to that fellow is 2. Yeah, and it cannot be smaller than that because they are not connected, obviously. So okay. Yeah. Actually, yeah, but that's going to give you an upper bound for the distance. It's not going to give you the exact distance. I think this is part of the problem. This is like actually I must tell you upfront that checking distances in the Hasse diagram is a tricky problem. It's tricky, and you will see in some way that actually where we are fiddling with it. This is like my conjecture stated there originally is converted into a conjecture about these distances. And for instance, one of the problems is that like it looks nice, but actually if you start measuring distances, it depends a lot. Like the shape of the shape of the graph depends a lot on where you set your basis. If, for instance, if you set your basis here here at the top, and then you start sorting non-crossing partitions by the distance to the top, it's something very nice. It's called the Narayana numbers, and you can control it perfectly. But if you set the base somewhere in the middle for a larger n, it's completely different, and even the distribution of distances changes. So it's non-homogeneous.
So it's always going some bits and blocks and going some blocks.
Yes, but sometimes you can do all sorts of zigzags which are shorter, strictly shorter than the obvious thing which you could do, going up to the first place where they meet, which would be called the join in the non-crossing partitions. And so from any pi and rho, you can go to their join. So go from pi to the join, go back to rho, and this will give you an upper bound for the distance. But usually it's not with equality. No, I don't, and I suspect it's not easy to do. I suspect this for like this picture is deceivingly simple. When n grows, these graphs are treacherous. Okay, good. So anyway, so let me point out here that I have now introduced a new random variable. Well, in fact, two of them. But let's look at yn. Yes, yn is a random variable on nc of n square, measures the distance. Okay, and there are two facts which I want to point out here, that are connecting this business of Hasse diagrams to the meandric systems. So facts. One, that there exists. Gee, this is a reminder. This is not my most pleasant reminder of chalk talks. Yes. So there is a natural bijection which sends, so take a pi in non-crossing partitions and get a sigma. So I'm using pi rho for non-crossing partitions in nc of n, and sigma tau for non-crossing pair partitions in nc of 2n. Yeah. Okay. So okay, and there is a natural bijection which is goes by so-called fattening. Well, of course, there are many bijections since both sets are counted by the same Catalan number. But this one has the following property, that it converts the problem about components of meandric systems into measuring distances in the Hasse diagram. Yeah. So this is my second fact, that if I have pi rho in nc of n, and if I let sigma tau their fattenings, which are therefore pair partitions of twice as many points, then the number of components of the meandric system on the fattened things is n minus the Hasse distance, this geodesic distance in the Hasse diagram between your original pi and rho. Okay, and this fact, yeah, this actually was proved by some people around maybe like 2005 or 2006. This has the consequence that so here this was my random variable x on nc2 of 2n. Whatever I want to know about it, I can know by looking at the other random variable y, which is on nc ncn nc over. Yeah. Okay. So the consequence is consequence. So if I let yn so it takes values in. So you can see that actually the maximal, the diameter of that graph, you can prove it is n minus 1. Well, it also follows from here, yes, because the number of components of a meandric system is between 1 and n. So n minus it is between 0 and n minus 1. Yeah. Then if you look at this relation and you take expectations, you get that they are connected in this way. Yeah. So then the results from my paper with Yen and Doron are converted to putting bounds so lim inf of EYN over n is greater or equal 0.5. Where do I and well let me squeeze here lim sup of EYN over n is less or equal 0.83, right? That's 1 minus the bounds which we had before. Yeah, and I said that I'd like to follow the lim inf which was giving 0.17. So equivalently, I now follow this lim sup of expectation of yn divided by n. Yes, and I'll follow how that comes about. Yeah, and so what's this? So E of yn. This is an elementary thing. It is the average distance in the Hasse diagram. You take that graph, you measure all the possible distances. There are Catalan square of them. Take the average. This is E of yn, and our conjecture, now proved by these other people, is that this average number of this average distance is like a constant times n, and here it's a bound that we could prove by using R transforms. Yeah. I don't remember monotonicity. No, I don't. I had a summer student who did ample simulations. Yeah, so but he was using n like 10,000, and there was nothing rigorous there. He was just kind of coming up, but coming out consistently that well, anyway. So the limit appeared. Yeah. Okay. Okay. So I'll follow this one which I boxed, that lim sup. Okay. And here is actually like why do we get a, so we get a limit, real limit, but for something else. Yeah. So let's make this observation, which is actually exactly Jamie's question. So pi rho in NC of n. So if I look at this new random variable, which is the distance, okay, I can bound it with triangle inequality exactly in the way Jamie was suggesting. Yeah. So I go to the join. Yes. So the join is the smallest upper bound of pi and rho with respect to the partial order which is considered there. Okay. And why is this good? Well, actually, it is good because here it's a distance between two partitions where this one is bigger than the other one. And then when you have this kind of situation, like you have, I don't know, you have this one bigger than, say, the minimal element of the block, always the distance is really measured by going straight down. So there is one exception, like when computing distances, this is one case which is easy, namely if they're sitting one like one is less or equal than the other, then you measure the distance as the difference between number of blocks, because every time you do one block more. So here you increase the number of blocks by one, here again by one. So the total distance, if you don't do zigzags, is just a difference in the number of blocks. So then therefore here it is okay. So I hope I'm putting it correctly. So this first distance, yes. So pi has more blocks because it is obtained from this other fellow by breaking. Yeah. Okay. And this one is rho minus. Okay. So therefore, this is absolute value of pi plus absolute value of rho minus twice. And here is actually I wrote there on the board besides yn. Actually, I'm interested in Zn. Yeah, and Zn is the one which is written there. Yeah. So Zn measures how many blocks there are in the joint. So if you do the smallest possible common upper bound for pi and rho, and you count the number of blocks, that's Zn of pi and rho, and it appears here twice. Yeah. Okay. So then if I do my calculation of expectations, then what I get is that the expectation of yn, yeah, I get a formula, but it's just gonna be with an upper bound. Yes. So the expectation of yn is less or equal the expectation of number of blocks in pi taken separately plus number of blocks in rho taken separately minus 2 times the expectation of Zn. Okay. And what I'm arguing next is that actually this one and this one, well, they are clearly equal to each other, but by symmetry. But I can say more. These one are, each of them is n plus 1 over 2. And why is that? Because, well, pretty much. So this is a one variable thing. Yeah. So just take a random non-crossing partition and count its blocks. And the fact is that not by coincidence this Hasse diagram has a top-down symmetry. So always there is a complementation map, the Crevaras complementation map, which I suppose may have appeared already in people's discussion here. Yes. So always you can group every pi with its complement, and together they have n plus 1 blocks always. Okay. So then using this top-down symmetry of the graph, you get this. Yeah. So n plus 1. So now actually this shows that what we have to do, well, for this upper bound that I'm looking at is kind of find something about Zn. Yeah. And Zn, actually, this is the amusing thing. You can compute the limit precisely. Okay. For Zn, you can compute the limit precisely. So main point in our paper, we can prove that this limit, yeah, so obviously you divide by n, yeah, of course I could do that here, yeah, and here this term has an actual limit, yeah, which we can compute. It is 16 minus 5 pi divided by 16 minus 4 pi, where pi is 3.1415, etc. Pi is no longer a partition here. It's the number, yeah. Okay, and the consequence is that then the lim sup of E of yn over n from that inequality which I had over there, yeah, this is 1 minus 2 times the limit which I place for the z's, which is this number, yeah, okay, and you get something which you estimate to that. This is how 0.80. This gives 3 pi minus 8 divided by 8 minus 2 pi, where fortunately 8 is indeed caught between 2 pi and 3 pi, and this is smaller than 0.83. Yeah, so what I'm showing is that actually the Zn, yeah, this is actually the what I did was a number of reductions to actually showing that I can compute this. Yeah, okay, and this is done by looking at some R transform gadgets. Yeah, this is what I want to sell. Yeah, so yeah, actually I have 10 minutes, 15 minutes, 12 minutes. What's my? Oh, I'm good. Yeah, I can go for 20 minutes and then you can ask no questions. No. I don't want that. No. Okay. I can ask the questions and then run here and then answer the questions. You know, like I can be. Yeah. Okay. Good. So no, because now I finished the part 2 of my talk, which the conclusion was that this is the thing to look at. This is what we want to look at, and then part 3 of my talk is saying how do we use the R transform, yeah, to get, yeah, I don't know, let's call this nice limit, let's call it diamond. Yeah, so how do we get diamond by using R transform methods? Yeah, so what, okay, and we do moments and precumulants. Yeah, and I'd like to do like slightly different. So I'd like to do them. It's nicer if I phrase them for quote unquote distributions, that is linear functionals, instead of talking about elements. So let me just say this calligraphic D, the collection of all linear functionals which are normalized. Yeah, okay, which you can think of as kind of mu is given by some probability measure with compact support, perhaps, where this tells you how to integrate polynomials. Yeah, okay, and here actually this mu has, well, actually, so every well, maybe like let me do this well. So this mu has an operation called box plus this D, yeah, and how does this go? Yeah, so how do we define the free additive convolution? It's called mu box plus nu. You represent mu and nu by 2 free elements A and B in some non-commutative probability space, and then you add together those elements. Yeah, so for mu in D, define the new functional mu box plus nu in D by putting, so since it's linear and normalized, I have to say how I, where I send my my power functions, the powers of the indeterminate, okay? So they are just phi of a plus b to the n, where a and b are two elements which are free. So in some abstract a phi, where a is following mu, so phi of a to the n is mu of x to the n, and phi of b to the n is nu of x to the n for all n. Yeah, and all this business makes sense. So always any mu and nu can be represented like this as phi of powers of a and b, with a and b free. Then a plus b to the power n, the phi of it is uniquely determined, and then this definition makes sense. And the main, so this is pretty much the same as like for instance what Peilan discussed yesterday, only that it's in terms of mu and nu instead of a and b. Yeah, but I find it nicer like that for what I'm gonna do here. Yeah, okay. And now let me also introduce this notation, yeah, which I think is like in Jamie's course, that any mu has m mu, a moment series, yeah, which keeps track of this how mu what mu does to the powers of the indeterminate, yes, and these are the moments of mu, yeah, and of course they are the same as the moments of the A, which represents mu, yeah, so it's nothing new here. And then if you take the free cumulants of this A, yeah, then you get a series. Okay, I'll call it C, so that I don't disagree with how the DR transforms. So this is pretty much a DR transform, but it is normalized in this way, starting so like this homogeneous way, where alpha n is the free cumulant of order n of mu. And by free cumulant of mu, I mean the free cumulant of the A, which represents mu. Yeah, okay. And the fundamental fact which we have here, well, one fundamental fact. There are many fundamental facts, but one that appears here and Peilan showed yesterday, yes, is that when you do this convolution, this pre-additive convolution, then the free cumulants are being added together. Yeah, okay. So this is a sum at the level of coefficients, or a sum at the level of power series. Yeah, okay. Now the point which I want to make is just do another like little spin from here. Yeah, namely if you do mu with itself several times, you get these box plus convolution powers. Yeah, okay. So mu box plus n, yes, is mu pre-additive convolution with itself n times. Yeah, okay. And this implies, of course, so if you take cumulants, yeah, then what happens is that when you do the box plus n power, you rescale the cumulant series by n. Yeah. Now for that thing, n doesn't have to be an integer. So actually, what I like to say is that you can define convolution powers of real exponent. Yeah. So extension to exponents in 0 infinity, say. You define the convolution power t, yeah. So So for mu in my space of linear functionals and t positive number, define this convolution power, which is again in D, by requiring that this free cumulant generating function of the new distribution is t times the C of the original one. Yeah. So rescaling, rescale the cumulants by t. Yeah. And if you rescale them by n, you fall back here. Yes, because indeed this is what t equals n would do. Yeah. But it's important that you have a continuous field of possibilities here. Yeah. Okay. And okay. So now I can start telling you. So there are two gimmicks, two lemmas. So actually, one of them is very important, and it would be disrespectful to call it a gimmick. Yeah, but both are important, and made by people which I admire. So first of all, yeah, you can take a mu. Yeah. So that variable z, that random variable z, there is a lemma proved by Bian and de Hornoy in 2014. Okay, and says like this: take the mu, which is defined by forcing the moments to be square Catalan numbers. Yeah. Then for every t and every n in natural number, we have that this box plus convolution power t moment of order n is expressed as a double sum pi and rho non-crossing partitions in NC of n, t to the power number of blocks in the joint. So that's actually, this is the z of pi and rho, which appears here. Yeah. Okay. And if you want for sanity check, yes, make t equals 1, you get indeed that you have to start with the linear functional, which gives for moments the square Catalan numbers. Yeah. But yeah, and they prove this. That they are doing a somewhat peculiar thing, that they are doing free cumulants for classically independent random variables. Kind of a strange thing. Okay. So then I immediately observe that I can use this as an instrument towards working with my random variable z, capital Z. Yeah. Because I can consider a series of two variables. So let's make capital U of t and z to be the generating function. So it can be in short written, it is the moment series of mu to the box plus t. Yeah. Or if you want, yes, it is summation n from 1 to infinity. And here I must put the moment of order n, which I express with Bian de Hornoy. Yeah. So it is t to the pi join rho z to the n. Yes, this is a polynomial in t. Yes. So this is a series in z with coefficients polynomials in t. Okay. And
Question: Is there an analog of this lemma if 2 is exactly Catalan numbers, square Catalan numbers? How do you get from the square Catalan numbers lemma?
I don't remember. So well, actually, let me try to think if I think actually the way they proceed was vice versa, but indeed. So how do you do? So I think actually I don't think that I'm saying something which is illuminating, but I think their proof, which is a proof by combinatorics, goes by sorting out. So write this sum over pi and rho in NC of n. Write it as a sum over, say, tau. So write a double sum. Write sum over tau. Oh, and then second sum, summation over all the pi rows with which have the join equal to tau. T to the yes, but then now this is a multiple. This is a multiple of t to the number of blocks in tau. Yes, so this is constant now. This is t to the tau. So this goes out, and then here you have to count in how many ways some given tau can be written as a join of two other things, pi and rho, and there's a game going around there. But indeed, I don't think that I'm answering the question really, because yeah, well, what happens if you start with just Catalans? Yes, so that would be mu would be then the Marchenko-Pastur distribution, and the convolution powers then will be other Marchenko-Pastur distributions. So I don't know exactly. Yeah. So if here if here there's no square, then yeah, yeah, you have to write the yeah. Okay. Actually, I can. Yeah, I can. So let's call that one, I don't know, yeah, nu, yeah. So nu of x to the n equals cut n. This implies so all the free cumulants are plainly equal to 1. Yeah. Okay. So then the convolution power is summation t times z to d1. Yes. So when you do box plus t, then you get this. And now when you write the moment cumulant formula for this, yeah, because this is so if I write nu to the power box plus t, nu to the power box plus t of x to the n, this is what? This is summation, single summation pi and c to the n, and I must do a product over the blocks of pi. I get this. So this is the answer if instead of Catalan square I'm doing Catalan. Yeah, yeah. But yeah. So this one, let me tell you why this one is helpful though. Yeah. So this one is helpful because if I do the derivative with respect to t here, and then I evaluate t at t equals 1, then I just get the sum of these exponents. Yeah. So when you do derivative with respect to t formally, this exponent goes to the front. Yeah. But then you set t equals 1, so then the power disappears. Yeah. Okay. And the moral of there is that in that series of two variables, if I so then have derivative with respect to t at t equals 1, yeah, equals summation n from 1 to infinity. Okay, and here I get summation pi rho in NC of n, number of blocks in pi join rho, times z to the n. Yeah. Okay. This is what happens. Yeah. Which actually I can identify here. So this one, yes, this is modulo the normalization by Catalan number square. Yeah. This is the expectation of my Zn. Yeah, okay, good. So I am getting something. Well, doesn't look nice here because it's a partial derivative with respect to t at time t equals 1. But here is pretty much the generating function for the expectations that I'm following. These expectations of the z ends, now I have them caught into this generating function, and I can tell something. Let's call this formula star. Yes, which does. No, it's no longer an integer parameter. T can be real number. T, I was saying, this is important that we do box plus powers. That was an important step. That T can be any positive number. Say, I do extend it. I can and I am. Yeah, and I get this formula star. And indeed, there is an objection which you could make is that I replace this with something ugly. But now comes the other thing, which goes back all the way to Voiculescu, which says that there is a PDE satisfied by that U. Okay, but now U known to satisfy, and this is actually a very early paper, one of the first papers where Voiculescu was setting the basics of the R transform. Yeah, it's this T partial U divided by partial T equals U plus Z times U times partial U by partial Z, and this thing is divided by 1 plus U. Yeah, so, and this is the formula, say, double star. Yeah, okay. So you see, this is not specific to the mu that I have considered. This would be for any mu, yeah. And I can tell you in one sentence how you get it. You write the moment cumulant formula for this convolution power. And then on both sides on the moment cumulant formula, there's going to be t and z. You take partial derivatives with respect to t and z in that moment cumulant formula, and you see that both of them have some ugly term. You eliminate the ugly term between the two. And what comes is this. And one thing to look at, you see, so this is the derivative with respect to t in terms of something which only has derivative with respect to z. Yeah. So somehow this tells you that if you know perfectly, actually what I want to do is make the time t equals 1. So for t equals 1, then I get that, well, 1 is 1. So it's just this partial derivative at t equals 1. Yeah, of z. Yeah, okay. Let me, yeah, well, of z, yes, equals, okay. So what's going to happen? Well, you see, like when you make here the time t equals 1, this is stuff you know, because u of t and z was the moment series of mu to the power box plus t. But if t is 1, then this is just your original mu. So here you get m mu plus what you get here z times m mu. Derivative with respect to z is plain derivative m mu prime divided by 1 plus m mu of z. Yeah. So you see, actually, so double star gives me, yeah, where m mu is a very civilized series. Yes, m mu is the generating series of square Catalan. Okay, and now you run. So I want to push because I can't remember how much over time. So yeah, I've asked and answered all the questions. Huh? So anyway, so point is that you have star and you have double star. Yes, actually better double star would be here, because then they have the same left hand side. Yeah, okay. And then you equate the right-hand side here with the right-hand side there, and you extract coefficients of z to the power n, and you compute and you find our limit. Okay, and I am running over time, but I wanted. I don't know if you could forgive me for another, because I want to draw another picture. This is actually a question. I don't think it's, well, I don't know if it's a problem. But perhaps like this is this appeared yesterday when I was talking with Jamie and Octavio, and yeah, so here is a question which I can ask. Perhaps it's just an exercise. But okay, so consider the following picture. Yes, so for this workshop, I think it's important to consider this kind of picture. Yeah, and I'll only put 2 points on the outside, but I put 2 endpoints on the inside. Say 6. Yeah, okay. And then what I do is the following thing. So on the outside, so here these ones we connect them outside. Okay. Yeah. Let me, I don't know, use various colors. Okay, so these ones get connected on the outside. Yeah. On the inside, we do a random non-crossing pairing. So for instance, this one. Okay. And then in the annulus, we also do a random non-crossing per partition. Yeah. So say for instance, I do this. Yeah. I connect this one with this one. Yeah, and I connect these two, and I connect these two. Yeah, and look what a beautiful. So this is a connected thing. Yes, you can count. Okay, so I can now go and check how many connected components there are in all, and there is one. There is this wavy picture. Yeah, and I say this is exactly an annular version of the question that I was asking at the beginning, and I don't know. Perhaps it can. I don't think it can be easier than that, but perhaps it can be reduced to that. Yeah. So I say here. So question. Yeah. To finish with the question. Make a probability space. How many atoms? So say here there are 2 endpoints. And so let's say we stick to 2 points outside, two endpoints inside. This one can be done in Catalan n. These per partitions of the per partition of the inside disk. The annulus, if I'm not mistaken, should be 2n times the Catalan. Even though I'm kind of yeah, didn't yeah, from direct counting, but I'm sure that Jamie will correct me as necessary. Yeah. Okay. So that's the number of atoms. So do randomly something red inside, something purple in the annulus, and here just do this. Okay. Then what is the expected number of connected components? Yeah. So is it of the form constant times n? Yeah. Okay. So yeah, and as I'm saying, so this actually came out of the break discussion yesterday, and I think it perhaps it is just an amusing exercise. So I can't assess what's the level of difficulty, but anyway, it's a nice way to end. And look, there is an annular picture on the board. Good, thank you. And yeah, sorry, yeah.
Seems that all the questions asked and answered.
Yeah.
But if there's one question, like, yeah.
Would that make sense? Like 2 endpoints from
yeah, of course, you could, once you solve this one, then you can do 4 points on the outer circle, or 6, or generally 2m. Yeah, so you can, but I thought, okay, so let's look at this one, for instance. Yeah.
So sorry, I mean, these meanders are very native model. How they appear?
The problem originates with Arnold. And actually Arnold, what he was asking, which is a harder question. So if you look back at the original first random variable, which I considered, which was called xn, and was counting the number of connected components in a random meandric system, Arnold is asking, this is the famous problem of the meanders. What's the probability that it is only one connected component? So if the meandric system is only having one canal there, yeah, then you call it a meander. And actually, I don't think that anybody hopes to give a formula for this, but there is open. So what's the rate of convergence? So if you take this probability is this is okay. You divide by 16 to the n, which is the asymptotics for the square Catalan number, yeah, because it's a probability, right? But if you ignore that Catalan number square, then it grows like something, and that something is not known. And there are numerical estimations that thing which is not known is like 12.26. So 16 comes. This is the rate of growth for the square Catalan number. The Catalan number itself grows like powers of 4. Catalan number squared gives you this 16, and this is this mysterious constant, which to the power 1 over n, to the power n, is kind of following this number of meanders. Yeah, and the story is so Arnold gave this question in the 90s or in the 80s to his students Lando and Zvonkin. It appears in the book as well. Yeah, and then around, I believe it was around 1992. They had, or 1993 or something like that, they had a number of good results about that. Yes, but I think it's not, this one is, and I think this is the reasonable way to address. So if you want to study the random variable xn, you don't start with that. You start with the expectation. If you figure out the expectation, you ask what's the variance. You ask if it's Gaussian. You ask various things, but you don't jump to that. Arnold was motivated by algebraic geometry considerations. Like there's something called ovals in I don't know what kind of projective planes, which he was counting and correspond to this.
Okay, let's thank Andrew again. And,
your speakers today, they are talkative, huh? They
No,
never stop, huh? You have to